All right, welcome to our second half of part three for our video series for our lecture on Wednesday, April 5th. Again, this is kind of like a bonus information lecture, not something that I would ask you to ever recreate because it does delve into a little bit of Chem 220 topics. But again, I think it is worthwhile to see where on earth this relationship between pH, pOH comes from. So I'm going to derive it by talking about water. So let's start by talking about water. So as we know, water is a special compound. It's special because it has that high degree of polarity due to its bent shape and its super electronegative oxygen pulling unequally on those covalently shared electrons between each of the hydrogen atoms. And it's because of this innate polarity that we call it the universal solvent, right? We see that water is something that can dissolve quite a bit of substances, including things like ionic compounds, most of them, and our polar covalent compounds. And water also has some interesting properties like high specific heat capacity. It's more dense in its liquid form than in its solid form, et cetera, et cetera. We're going to talk about that later. But in general, water is interesting. And one of the ways that water is interesting that's related to pH, pOH, and in general the concept of acids and bases is that water itself is what we call amphoteric. This means that it can act as either an acid, meaning it could be a proton donor, according to our Bronsted-Lowry definition, or it can act as a base, being a proton acceptor, depending on what kind of chemical situation that water is found in. So amphoteric. Another amphoteric thing is the bicarbonate ion. That's why we use sodium bicarbonate to neutralize both acid and base spills. And if you want to talk about the chemistry of the amphotericness of the bicarbonate ion, come find me in office hours. But let's get back to water and let's ask ourselves, why is it that we think water is amphoteric? Like, why is it something that could be either an acid or a base? So you might remember from our neutralization reactions that when I write H2O liquid, I also sometimes write it as HOH. And the reason I do that is because I really want it to be obvious for us in our double displacement, where we have the acidic H plus coming together with the basic hydroxide to form our neutral liquid water, where this is our acidic proton. And this hydroxide is our basic hydroxide. So notice, water is composed of both a base particle and an acid particle. This is what makes water amphoteric. Now, another thing about water is that water very weakly autoionizes. In other words, it dissociates very weakly. And if we think about the definition of an acid or a base according to Bronsted-Lowry, which is what an acid or a base does, whether it's donating a proton or accepting a proton, If water is going to be able to donate this acidic proton, then it has to be somewhat detached from that acidic proton in order for it to be donated in the first place. Think like acetic acid. Acetic acid is a Bronsted-Lowry acid because it can donate that acidic H plus ion, and it can donate that acidic H plus ion partially because it is a weak acid, which shows only partial dissociation from the acetate ion and that acidic H plus ion. So if I were to write this autoionization of water, HOH, liquid, I would show a partial dissociation into our acidic particle and our base particle. So this is the autoionization or dissociation equation for water. Now, in Chem 210, anytime we want to talk about like how well something dissociates versus like how well, I guess just how well something dissociates, we actually quantify this. So we can quantify how weak or how strong our dissociation is by looking closely at this equilibrium that's established in the forward dissociation and reverse reassociation process that you and I call a weak dissociation. So this equilibrium, in general, any equilibrium, so states in equilibrium, are always described by some kind of equilibrium constant, K, and in general, if K is large, then the forward, in our case, the dissociation is favored. And if K is small, then the reverse, for us, the reassociation, is favored. And for water, this Kw, or equilibrium constant for the autoionization of water, is a value that's really, really small. Because again, when you and I think of water, we treat it as a liquid. We don't treat it as something that behaves like an acid, a weak acid, or a weak base, even though it kind of does. And the reason is because it's Kw, that equilibrium constant that describes how well water dissociates, is quite small. In fact, it is 1.0 times 10 to the negative 14. And this is something that has been measured in the lab, and that's molarity squared is the unit. Now, how we calculate these equilibrium constants is these equilibrium constants are always a product of concentration of products in proportion with the product of the concentration reactants, as long as our products and reactants are aqueous. Because again, if we're talking about like the concentration of a liquid, that doesn't really make sense because liquids are pure substances. They're not a particle that's found in something else. They're only aqueous. So if I were to then write this proportion of product over reactant, I would look at my dissociation equation and say, okay, well, one of my products is this H plus, so I'm going to have concentration H plus, times my other product, which is OH minus, and then I would divide that by my concentration of reactants. However, again, my reactant here, the thing that's dissociating or autoionizing is a pure liquid. So we do not include that in this K expression. Now I'm just describing this all for you so that I'm not just dropping math in front of you you haven't seen. I'm trying to talk you through what I'm doing. But if this all seems weird and new, it's because it is. We haven't talked about equilibrium in 210, nor will we. I'm just trying to show you where this relationship here between pH and pOH come from and why it is in general the pH scale ranges from 0 to 14. So it all comes from water. All right, so I'm going to rewrite this. I'm going to write this as 10 to the negative 14 molar squared is equal to concentration H plus times concentration OH minus. Because 1 times anything is just that anything, so I just dropped the 1 to make things less confusing. All right, this 14 number is locked up inside this exponent of base 10, so to undo that, I'm going to take the log base 10 of both sides. And anytime you take the log of something, its units disappear, so I'm going to go ahead and just drop my units here. And this becomes the log of my product concentration H plus times concentration OH minus. All right, now I got to apply some log rules. The whole reason I took the log of both sides is because I wanted to get this negative 14 exponent out of its base 10 power. So what I see is I see a cancellation of my log and my base 10, leaving behind simply the exponent. And then I've got log on the right-hand side, concentration H plus times concentration OH minus. Now I can use my log rules, which states that the log of a product is equal to the sum of those terms in the product. So I'm going to use that for this guy, the right-hand side. So I can now rewrite this as negative 14 is equal to the log of concentration H plus the log concentration OH minus. And if I get this 14 by itself, meaning divide by that negative 1, then I have 14 is equal to negative log base 10 concentration H plus. And I'm going to write this as plus negative log base 10 concentration hydroxide. Oh, wait a minute. Log concentration H plus, this is what you and I call pH. So I have 14 is equal to pH plus, and oh, hey, something else is going on here. The negative log of concentration hydroxide is what you and I call pOH. And so we have now derived where on earth this relationship comes from. It comes from water and its equilibrium or autoionization constant, its Kw constant. Now, if that was useful for you, great. If not, don't worry about it. If you got anything from this video, it should be that water is amphoteric, or what it means to be amphoteric. And let's see here, going back up to what we've got in our lecture plan. You know what? I think we are going to save this for some warm-up problems on Friday. the 7th. And then we will move away from aqueous reactions for a moment and talk about, in general, how we can look at quantities in reactions, which we call stoichiometry. So see you all tomorrow to wrap up our 9 solution problem lab, and then on Friday, we'll move on to our next topic.